Alright everyone, it's Mr. ED back with yet another video. Today we're going to be talking about topic 7, which is Le Chatelier's principle. And this section, folks, is going to be a bit more conceptual in nature. And what we're going to be looking at is how will an equilibrium respond if we made changes in, say, its concentration of the reactants or changes in concentration to the products. Additionally, we'll see what happens if we make changes in concentration to the temperature. We'll also have a brief callback to Unit 6, so that's a short review there. And then we will talk about changes in pressure, okay? Especially if we're looking at a gaseous equilibrium. So what Le Chatelier's principle is it states that an equilibrium will respond to counter any change imposed on it. Okay. Now, what that really means is, well, whatever you do or whatever I do to an equilibrium, it's going to do the exact opposite. So, if we're looking at changes in concentrations, with that in mind, if I increase the concentration of the reactants, then my equilibrium will counter me and do the exact opposite. So it will proceed to shift the equilibrium towards the product. So again, I increase concentration of the reactants. The equilibrium responds to me by doing, all right, well, we're shifting towards the products. And conversely, if I were to shift the concentration, or excuse me, not shift, but if I increase the concentration of the products, my equilibrium then immediately shifts back towards the reactants. So if we were to consider hydrogen gas is reacting with nitrogen gas and they form an equilibrium with ammonia gas, what ends up happening, right? If I just illustrate this, right? If I increase the concentration of, say, my hydrogen gas here, right? What's going to happen according to Le Chatelier's principle is, well, I've increased the concentration of a reactant. Well, then the equilibrium will shift back to the products, okay? Now, the opposite is true. So if I were to increase the concentration of NH3, then the reaction would shift back towards the reactant. So again, it goes back to whatever you do, the equilibrium, according to Le Chatelier, the equilibrium does the opposite. So that's going to be the running theme of today's notes, okay? Let's take a look about temperature. So if we increase the temperature, specifically the energy of the environment, so this would be, if you think back to topic 0 of this presentation, remember when we were talking about a reversible process, any infinitesimally small change to the surroundings, aka the environment, you could have something that's reversible. And we know equilibriums are in fact reversible. So, this is just tying in that subsection topic 0 to now. Okay, so it's a callback to now, and it's also going to be a callback in just a moment to Unit 6, and you'll see what I mean. If it's endothermic, and you increase the temperature of the surroundings, then the reaction will shift towards the products. So you'll notice, guys, that I have heat written here as a reactant. So when you have heat written as a reactant, that means delta H was in fact positive, right? Because delta H, right, that's enthalpy, that's our heat energy, right? That means it's going into the system. And so if we were to increase heat and it's at endothermic, so we increase the heat of the surroundings, well, how does the equilibrium respond? It responds by shifting to the reactant, or excuse me, to the products. And again, why is that? Well, delta H is positive, and when delta H is positive, we can think of heat energy is essentially as a reactant. It's going into the system. And if we increase that heat, we put more energy into the system, we drive the forward reaction, so the equilibrium shifts to the products, okay? Now, for an exothermic reaction, if we increase the temperature, the reaction will shift towards the reaction. So this time, guys, if we're taking a look here, right, this would be in a case where, of course, delta H is going to be negative, right? And you'll notice where we put our heat now is the heat is on the product side because heat is released in an exothermic reaction, right? And so now we can think of heat as part of the products because delta H is negative, right? Well, if we go back to our Le Chatelier temperature shifts, right? If I'm increasing the heat of the surroundings, well, it's just like heat being a product now. So if I increase the heat of the products, right, that's where heat is. I'm essentially increasing that quantity. How does the equilibrium respond? Well, it's going to shift the equilibrium to the reactants, right? So it's going to drive, in other words, it's going to drive the reverse reaction because heat is considered a product as this is an exothermic reaction. So again, the callback that we're having to unit 6 here with our enthalpy, right, our heat energy essentially, right, guys, is this idea that after we recognize the sign, so if it's positive, we can think of heat energy as a reactant we're going to put heat into the system to drive the forward reaction, and if we increase that, it will shift the equilibrium to the products, okay? Conversely, if we have an exothermic reaction, when heat is being released, right? When heat's released, that we're going to consider that a product now. So if I increase my heat energy, right, or if I increase the temperature of the surroundings, then my heat energy goes up, but since it's now a product side, it shifts the equilibrium back to the reactants, okay? So again, we're kind of tying Unit 7 together with Unit 6 now. We're having a lot of callbacks. I'm hoping that we're starting to see that, you know, our units here are not microcosms. They are all connected, and we're coming to a point in the curriculum where we get to start having these callbacks and we get to see where these connections are being made, okay? Now, let's continue on and talk about changes in pressure. And our first bullet point of notes here, guys, is a callback to Unit 3, specifically the gas law sections in Unit 3. And if you remember, we said that gas pressure and volume are inversely proportional. That is to say, right, that if I increase my pressure of a gas, the volume of the gas would decrease, right? They're inversely proportional. Pressure and volume are going to move in opposite directions, right? Well, that's important as we come up with how Le Chatelier's principle is going to work here. So if we increase the pressure of a gas, then the equilibrium is going to shift towards the side with less moles of that gas. So I'm increasing my gas pressure. The way that my equilibrium responds is it goes to the side with less moles of the gas, okay? Now, if I increase my volume, and remember what that means. If I'm increasing volume, I'm decreasing gas pressure, right? So to counter that, if I increase my volume, aka I decrease my pressure, then the equilibrium is going to shift to the sides with, in this case, more moles of the gas. So if we're looking at this reaction here, again, it's been the Haber process, hydrogen gas reacting with nitrogen gas is in equilibrium with ammonia gas, right? And let's just say I'm imposing that I want to increase my gas pressure, so P is going up. Okay, so now if I'm increasing my gas pressure, okay, what happens to this equilibrium? Well, the equilibrium is going to shift to less moles of a gas. So we have to count the moles of a gas, right? Well, in order to quickly see that, guys, you look at the stoichiometry coefficients in front of the substances in your chemical equation. So there's a 3 in front of H2. There's an invisible 1 in front of N2. So on the reactant side, we have 4 moles of a gas. And then we go to our product side, right? So I'll draw a little line there. And there's a 2 in front of ammonia gas. So we have 2 moles of a gas there, right? So what happens is by increasing pressure, how does that shift the equilibrium? Well, we saw that the product sides have less moles of a gas. So the equilibrium for this reaction is going to shift to the products, okay? Again, we're seeing all these callbacks from previous units. I really want you guys to be taking away with that we're in a point in our curriculum where we're going to start seeing callbacks. We're no longer seeing microchasms that this only worked in this unit. No, we're connecting everything together now, okay? Let's continue to some example problems. So here is what we're going to do. We're going to find how the equilibrium is going to respond if we A, increase the pressure, B, we increase the temperature, and then C, if we add C8H18. So we add more of that. So our chemical equilibrium is carbon monoxide and hydrogen gas is in equilibrium with octane, C8H18, plus some water. We have a value of delta H is negative 1,265 kilojoules. Guys, remember what that delta H value is telling us. It's identified to us that we have an exothermic reaction. Right, this negative sign here is, of course, exothermic. And then that means I can write as a product that we have plus heat, because heat is giving off when it's exothermic. Why am I writing it like this? Well, we're talking about temperature in our second bullet there, so we might as well discuss it, right? Now, it says increasing gas pressure. So we increase gas pressure. We know that the equilibrium is going to shift to the side with less moles of a gas. So on our reactant side, we have, what is this, 17 and 8. We are looking at 25 moles of gas on our reactant side. And on our product side, we're looking at 1 plus 8. So we're looking at 9 moles of a gas. So if we think of it like this, if we increase our pressure, the equilibrium is going to shift to the products. Okay, so the equilibrium will shift to the products because there are less moles of gas over there. Okay, our next problem is increasing temperature. So remember, guys, we already discussed that this reaction is exothermic. So since this reaction is exothermic, heat, we can think of it as a product. So if I increase my heat here, okay, heat is going to then drive the reverse reaction and shift our equilibrium to the reactants. So our equilibrium, if we increase temperature, will shift to the hold on, guys, I spelled equilibrium wrong. I'll be right back. Okay, so as I said, we increase the temperature. The equilibrium is going to shift to the reactants because, as again, this reaction is exothermic, so we're going to think of heat as a product. Well, if we increase the product, the reaction shifts back towards the reactants. Okay. Now, our next one is we're going to be adding octane to this chemical reaction. And if we add octane to this chemical reaction, we know we're increasing the concentration of it, right? So we're increasing the concentration of a product. It means the equilibrium is also going to shift back to the reactant. So the equilibrium here will shift in our third bullet back to the reactants. All right. So that's our first problem. Let's take a look at another one. All right. So this one is going to be a little bit more tricky because, you know, we're looking at a separate equilibrium. It's tricky in the sense, guys, that it's a heterogeneous equilibrium, right? We've got a liquid phase here and we got a solid phase here. So it's going to be a little bit more tricky, but nonetheless doable. So again, we're going to be predicting how the equilibrium is going to respond if we decrease the pressure, we decrease the temperature, we remove some oxygen, and then we add that molecule here, C6H12O6, is called glucose, okay? So let's dive into this problem, all right? First thing, guys, is it's saying that we're going to be decreasing gas pressure, right? So what happens when we decrease gas pressure? So if we decrease gas pressure, guys, just remember that the volume is going to increase, right? And when we increase volume, the equilibrium is going to shift to the side with more moles of a gas. Well, when we're analyzing this equilibrium, we know that water and the glucose, right, they have no effect on this equilibrium, right? They're not going to shift it in either direction. Only gases or aqueous solutions can do that. So water's out of here and glucose is out of here because, again, liquids and solids do not affect the equilibrium, okay? So if I decrease pressure, I have on my if I decrease pressure, we're looking to increase the volume, and if volume increases, we're going to shift the equilibrium to the side with more moles of a gas. Well, I have 6 moles of a gas here, and I have 6 moles of a gas on the product side. So we've got 6 moles of a gas as a reactant to 6 moles of a gas as a product. You'll notice that the moles are equal. So since the moles are equal, there is no change, right? So since the moles of gas are equal, no change to the equilibrium, okay? There are no change to the equilibrium there, guys. Okay, so now let's see what happens when we decrease temperature. So you guys are going to notice that this reaction is endothermic, right? Because it's a positive delta H. Well, since delta H is positive, again, we can just add our heat energy to the reactant side, right? Because we have to put energy into the system. But we're decreasing it this time, right, guys? So the heat energy is going down. So if I'm decreasing heat, what happens to the equilibrium? It shifts to the reactants. So in this case, we're going to shift the equilibrium to the reactants because we are lowering the temperature, and that essentially is going to lower our heat energy. And then if we lower it, it's going to shift the equilibrium back to the reactants. All right, so our next one is we're lowering the concentration of O2. So O2 is going down this time, right? So again, your O2 is going to be decreasing here because we're removing it out of our equilibrium vessel. Well, what does that do? Well, if I remove oxygen from the equilibrium vessel, it shifts the equilibrium to the products. So we remove O2, we're shifting the equilibrium to the products. Okay. And our last one is we're adding glucose, right? So we're adding glucose. Glucose is a solid though. So since glucose is a solid, folks, no effect on equilibrium, right? Solids don't have an effect on equilibrium, so this will have no effect on this equilibrium, okay? All right, so again, what's the summary about Le Chatelier's principle? Any change that you impose on equilibrium, what does the equilibrium do? It does the exact opposite to counter you, okay? So let's do one more example problem, except this is a you do, we review. So we have the equilibrium of water. Liquid is in equilibrium with steam. Delta H is 44 kilojoules. And I want to know what happens if we decrease the pressure, we decrease temperature, and we add some water. So go ahead, guys, pause the video and try this one on your own. All right, guys, and I hope you saw that if we decrease gas pressure, the only way that the equilibrium can shift is to the side of more moles of a gas, that being the products. So we increase the volume, if we increase the volume, we're shifting to the products. If we decrease the temperature, since this is another endothermic reaction, so if we decrease that temperature, the equilibrium is going to shift back to the reactants. And then finally, if we were to add water, liquid water, there is no net effect on the equilibrium because, of course, liquid water is, in fact, a liquid. And with that being said, guys, that is the end of today's video. If you have any questions, shoot me an email.